It means it's working? Excellent. All right, so as I say, I'll leave it to you folks to tell me mostly what I should talk about, but I've had a few suggestions, and those suggestions are that I say a few more words about black hole thermodynamics, finish up some leftover comments from last time, and then maybe say a little bit about the holographic principle. Okay, so what I think I'll do, let me start by saying that I've listed here two more references you may want to write down. One is actually a brand new reference. This review article on black hole thermodynamics by Thibaut Damour was placed on the web yesterday. And I have had a chance to browse through it only briefly, but it looks like it contains a lot of interesting material. So you may wish to write this down and have a look at it. I also realized when I was writing this down that I had forgotten to give you another standard reference on the subject of black hole thermodynamics, which is by Bob Wald, the same person who wrote the big, thick general relativity textbook. And since it was the last-minute thing, I didn't look up the exact reference for you. But if you search on the web for Living Reviews in Relativity, which is an online journal, you'll find exactly one article on black hole thermodynamics. It is by Robert Wald, and it's from 1999 or 2000. This is a really lovely article, but I should warn you that it is written assuming a lot of prior knowledge. In fact, some people believe that Bob wrote this article assuming that the reader had both read and digested his textbook. So I just warn you of that. All right. So maybe I should start by just asking if there are leftover questions I should answer from last time before I try to do anything halfway prepared. Are there any questions from the last couple of lectures that you'd like me to go back over? Or you'd like me to just do some new stuff? Okay, new stuff. Very good. On we go. All right. Well, let's just remind you where we finished last time. We finished last time by noting that the Euclidean Schwarzschild solution has a circle, and do those of you in this room know that S1 is a circle? Okay. A circle at infinity of length. What was the length? The length was 8 pi times the mass. And therefore, this correspondence we had with Euclidean field theory and temperature suggested that these black holes have a temperature equal to 1 over 8 pi m. Okay, that's where we finished up. So temperature is very exciting. As I mentioned, this is a property that Stephen Hawking found for black holes via a longer calculation. Let me just say a few words about what Hawking did. I'm not going to go through the details here. But going back to this picture we've been drawing for a black hole, okay, what Stephen Hawking found was that, well, okay, Tony Z told you a lot about quantum field theory. But Tony was basically telling you about quantum field theory in Minkowski space, in empty, flat spacetime. You could also do quantum field theory in a black hole spacetime. And it turns out that when you do, you find something interesting. In the black hole spacetime, it turns out that when you study any quantum field theory, and there are now general theorems that say this is really true for any quantum field theory, the space is sort of not very quiet. That is, in Minkowski space, when you study Minkowski space, well, let me not worry about how to draw the Minkowski space, but in Minkowski space, it's really empty. There's nothing happening. The vacuum state is the vacuum. It contains no particles. There's no energy flowing around, right? It turns out that when you study quantum field theory in the Schwarzschild geometry, the analog, if you like, of the vacuum state is it's an even more exciting place than is the vacuum in Minkowski space. It turns out that it does contain particles, even in what you might call the vacuum state. It contains a flux of particles flying outward toward infinity. Okay? In fact, it turns out that the flux of particles coming out of the black hole is exactly a thermal flux of particles at temperature 1 over 8 pi m. So when you do quantum field theory in this space-time, you find that energy is carried by these particles off to infinity. Okay. Now, I should warn you that when you do quantum field theory in general situations, the correlation between particles and energy is not as direct as it is in Minkowski space. This is something I don't have time to get into. If you read the reference I gave you by Ted Jacobson last time, it'll talk more about that. But the particle-energy correlation is less direct. But still, I guess I should make the comment, someone, in fact, I think did ask me, well, if these particles are flying out from the black hole, did they come out of the black hole itself? Or did the energy carried by these particles somehow escape the black hole? After all, we said that a black hole was something that nothing could escape from and no information could cross. Well, it turns out, I'll just give you the answer to this. I certainly won't go through the calculation. But it turns out that what's happening in Hawking's calculation is that these particles are actually being created dynamically, if you like. And they're being created in a region outside the horizon. And in fact, if I was trying to draw a more accurate picture of that, I would draw in one of these hyperbolas we discussed before. And they're actually being continuously created all throughout this region that I will shade with a different color so as we don't get it too confused. So in some sense, particles are being created all throughout this region. Okay? And interestingly enough, that's great. Particles can be created. That's one of the things that Tony taught us about quantum field theory. Particle number is not in general conserved. And it turns out that this is a case where that happens. On the other hand, energy is conserved, of course. Right? Energy is conserved. So if there's energy coming out, you might ask what the story is there, because certainly I'm not going to tell you that energy is created in this region. Energy is conserved. It's never created. Okay. What turns out to happen is, through another interesting effect in quantum field theory, I think I mentioned this briefly before, you can actually have negative fluxes of energy. So what happens here is that the vacuum, if you like, separates into an outward positive flux of energy and an inward negative flux of energy. Like so. So that if left to its own devices, indeed, positive energy is rated to infinity, and the black hole will shrink because it's now absorbing a certain kind of negative energy. But, as we mentioned before, this process by itself does not in any way involve energy moving from positive energy moving from the inside of the black hole out to infinity. Instead, it involves negative energy moving from the outside of the black hole inward. Okay. Yes?
The horizon is all over the line, but the intersection of the two horizons is especially. Do you know about that?
Well, we could talk a little bit more about what happens when the horizons intersect. It is a slightly interesting place mathematically, but it's not very interesting physically. And the reason it's not interesting physically is that I'll remind you of a comment I made before, which is that what I've drawn here is an idealization of a black hole. It's called the eternal black hole. It's one that was there from the beginning of time. Most of the black holes that we really wish to discuss are black holes that form at some finite time in the universe. And for such black holes, it turns out that most of this diagram, in fact, everything below this orange line is irrelevant. You want to throw it away. And so I'd be happy to talk to you about what happens here, but probably it's a discussion best left for some private setting someplace, because in some sense it's really not relevant to real black holes, and so we probably shouldn't take up our time with that. Yeah?
Do you have some sort of physical way of thinking about negative energy? Or do you do that anywhere else? It's just such a strange concept.
It is a strange concept, and it's the one that makes the black hole story very complicated. I could, if we had lots of time, I could go through this. But but unfortunately, it would take a long time to develop the technology. Let me mention two things, just to give you a feel for it. First of all, you're used to the idea that energies in quantum field theory are uncertain, that there are fluctuations in energy are allowed as long as they're reasonably short. Now, because this is a fluctuation, there's no reason why it can't be negative. if you like. So it might be natural to you to say, oh, perhaps negative energies can exist, at least for short periods of time. And indeed, if one studies quantum field theory carefully in Minkowski space, even in flat spacetime, one does find that this is so. More precisely, if one works in Minkowski space, it turns out the total energy is always positive, but the local energy density, what we might call rho, or the energy per unit volume as a function of position, okay, can in fact be negative in small regions of space and for short periods of time. This is, as I say, this requires more technology than we have at hand yet to actually go and calculate. But it turns out that even in Minkowski space, with a simple, say, 2-photon state for the Maxwell field, one can find examples of this phenomenon. So this is a consequence of this effect. Okay. Now, it turns out that those fluctuations, if you like, are naturally amplified in the presence of a black hole. And why is that? Well, it turns out that in a certain sense, if you are inside the black hole, it's natural to have negative energy even in classical physics. Okay? Let me say just a few words about this. This is, again, something we don't have the time to give the full technology for. But in this school, Noether's theorem, the connection between symmetries and conservation laws, has been discussed, right? And you are likely familiar with the idea that energy is the conserved quantity associated with time translation symmetry. Right? Is this familiar? Okay, well, if you don't know this, I leave it as an exercise to check that the time translation, sending t to t plus a, if you consider that symmetry and apply Noether's theorem, the conserved quantity is nothing other than the usual recipe for the Hamiltonian, which is the energy. Okay, if you go back and look at the equations, that'll become clear rather quickly. Okay, so what that should say to you is that energy has to do with the existence of a symmetry, time translations. Now, in Minkowski space, we have time translation symmetry, so we have lots of energy conservation. In general relativity, when the space-time itself can become curved and can change with time, there can be problems with time translation symmetry. It's not always useful. Okay. The Schwarzschild solution, or black holes, happens to be such a case. And how can I show you quickly that's the case? Well, roughly speaking, outside the black hole, time translations are normal. They behave much like in Minkowski space. Okay. But inside the black hole, there is no time translation symmetry. And that is actually somewhat clear from this diagram. Recall that we discovered that this lovely little wavy line I drew is the line which says that those spheres we talked about a lot, the spheres that are spheres around the black hole outside, all the spheres in the space-time collapse to zero size here. Whereas earlier, on some other hyperbola, r is not 0. And in particular, on the horizon, r is equal to 2m. So what we see is that inside the black hole, the shape of space itself is changing with time. R goes to 0 at a finite point in the future. Thus, we certainly don't have the usual kind of time translation symmetry. Okay. Now, it turns out, okay, so that tells you that energy is allowed to do funny things inside of a black hole. I'm getting to that, thank you. Well, there is no symmetry which acts locally inside here like a time translation symmetry. There is, however, a global symmetry of the black hole, which corresponds to time translations on the outside. Okay? And just to see that that should be true, let me quickly go back to the Minkowski space story. Or more properly, to what we call the Rendler story, where we looked at acceleration horizons in Minkowski space. Okay? Recall that this is an analog of what's happening near the horizon in the black hole. And that includes inside. Okay? So this space-time, it's Minkowski space. It has lots of symmetries. Okay? We don't want to consider the usual time translation symmetry because this picture is only a good description of our story there inside these hyperbolas, right? Close to the horizon. And if we applied a usual time translation, we'd move the hyperbola, so that wouldn't be good. But there is a symmetry of Minkowski space that leaves these hyperbolas intact. And that's a boost symmetry, right? The usual change of reference frames in special relativity, where we would change from some t x coordinates to some other observer, t prime x prime. If you're not familiar with this, let me leave it as an exercise. But the usual change of coordinates in special relativity from one orthonormal frame to another, from one observer to another, preserves these hyperbolas. It just moves points along them like so. Okay. So there is, this symmetry, in fact, does carry over well to this case. Okay. So there is a symmetry, and outside the black hole, in this region, you can see on the diagram I've drawn that it looks like you're just moving things more or less forwards in time, along a curvy path, but, close enough. So outside, it has all the properties you would expect of a time translation. But what about inside? Inside, it's sliding things horizontally. So inside, it has the properties one would expect of a space translation. Okay? And do you know what is the conserved quantity associated usually with space translation symmetry? Momentum. Right. So as a result, inside the conserved quantity is more like momentum. And it certainly wouldn't bother you if I told you I had a particle with negative momentum. Yeah. Right. Okay. So this is the basic flavor of the story. Inside the black hole, the quantity which interacts with what you would call energy outside is more like momentum, and it can have either positive sign or negative sign depending on which way the objects are moving. So the only trick is to get some interaction between the outside and the region where negative energies are allowed. So quantum field theory allows us to do that by basically having a small fluctuation where the energy is also negative outside, which lives only a short proper time and then hops inside to where it's allowed to persist classically. So if you like, it's a kind of tunneling effect. Only sometimes this is heuristically described as tunneling of stuff from inside the black hole outside. I find it much more useful to describe this as tunneling of negative energy particles from outside to inside. That's certainly the way that the energy flows. Okay. So that was a broad brushstrokes kind of picture. Didn't include many details. Is that enough for now? Would you like to ask more about it? That's okay for now? Okay. Very good. So let me move on. So this is the sense in which black holes have a temperature. Well, if they have a temperature, one might suspect that they would also have all of your other favorite thermodynamic quantities. Okay? And the most interesting thermodynamic quantity to many people is the entropy. So let's talk about black hole entropy. Okay? And I'm going to do a very simple calculation of black hole entropy. for the Schwarzschild black hole. I'm going to do it using thermodynamics. You may recall the first law of thermodynamics, which says that the change in energy is equal to temperature times the change in entropy. Okay. Is this familiar to everyone? Is there anyone who doesn't recognize this? You might perhaps know this better as the definition of temperature. T is defined to be, usually it's written 1 over T is defined to be ds dE. Or you might know it better in terms of the definition of entropy. ds is equal to the amount of heat that flows into a system divided by the temperature. But it's all the first law.
You combine the first and second
No,
law.
no, this is just the first law.
How come you got entropy?
Well, perhaps it's a matter of convention, but in the way that I am used to writing the first law, one writes it in terms of entropy. Okay. Yeah. What's that? Yes. There are often other terms like P, dV, and so forth. Okay. So in fact, let me say it more precisely. I'm really going to do this not at constant volume so much as at zero pressure. Okay. Yes, there can be other terms. I'm also going to do it at, there are a few other things I'm holding fixed as well here. This is the simple form. Okay. Really, I guess you'd say this is a combination of what other people might call the first law and the definition of entropy. So, yes, one might have written dq here instead of... Okay. All right. So, and I can do this because, of course, I know the energy in a black hole. The black hole we take to be at rest, so its energy is just m. Or if I hadn't set c to 1, it would have been mc squared. But I have set c to 1, so it's m. Okay? So, dE is dm. But it's also T ds, or in other words, ds is dE dm over T, which is dm. Let's see. 1 over T is 8 pi m. So this is 8 pi m dm. So if I simply integrate this up from 0, making the rather natural assumption that a black hole of 0 mass should have 0 entropy, okay, what I find is that the total entropy in a black hole is, well, we can all integrate 8 pi m dm. It's none other than 4 pi m squared. Yes? Okay. Now, it's convenient to go back and express this in terms of the size of the black hole. And you may recall that the Schwarzschild black hole is a size, r equals 2m. So what is this in terms of r? Well, 4m squared is just r squared, so this is pi times r squared. Whoops, r squared. Okay. Traditionally, one writes this in terms of the surface area of the black hole. The black hole is a sphere of radius r, so the area is just 4 pi times r squared. So this is a over 4. Okay. And the reason one writes it this way is that although I have by no means proven this to you at this point, this is in fact the generic, or perhaps the general, expression for black hole entropy. That is to say, I have so far considered a particular kind of black hole, the Schwarzschild black hole, which is distinguished by, well, first of all, it lives in 3 + 1 dimensions. Second, it has no electric charge. And third, it's not spinning. It's just sort of sitting there in space. Black holes can have electric charge. They can spin. You can have more complicated versions in higher dimensions, all sorts of things. But it turns out that for any black hole, or black string, or black membrane, or black p-brane, okay, one can show in general that the entropy always takes the form a over 4. Okay. There is, in fact, a lovely calculation using the same Euclidean methods that we talked about earlier this week, which gives exactly that answer. And if that's of high priority to the audience, I can go through part of that calculation later in this hour. But of course, it will mean that we don't get to something else. Okay. So this is an interesting answer. Why is it an interesting answer? Well, first, let me just show you that it's consistent with things you know. Actually, I'm not going to do all of it, but I gave you on that list of exercises I hand out a homework assignment, which is to go back into these expressions for t and this expression for s and figure out where the factors of h bar, g, and c went to. Okay? I've done these calculations setting h bar, Newton's constant g, and the speed of light equal to 1. Okay? But it often helps physically to understand where they are in these expressions. I will leave that for you to sort out. It's just dimensional analysis. But I will tell you two interesting properties of what happens as h bar goes to 0. First thing that happens as h bar goes to 0 is that the temperature of the black hole goes to 0. That's good. After all, I claimed that this Hawking radiation was some kind of quantum effect. Okay? The second thing that happens, which actually you can guess from the first one, you notice that S involves 1 over t. So if t is going to 0 in the classical limit, you would expect that the entropy goes to infinity. Okay? So there are h bars hidden in this expression such that in the denominator, such that as h bar goes to 0, the entropy becomes infinite. Right. Yes. Okay. Maybe I'll even show you this h bar just for completeness. I'll show it to you first in a place where you know it exists. If I had done not Euclidean field theory, but Lorentzian field theory, and looked at this object, where's the h bar here? Where does the h bar go in? It's h times t divided by h bar, right? Okay. So I compared this with e to the minus, beta h, and I said that beta is a length. Aha. Well, in relativity, lengths are as good as times, right? So that means that in terms of dimensional analysis, this quantity here, beta h, acts just like this one here. So there should be an h bar here, right? But the temperature, I said, was 1 over beta, so it's really h bar over beta. And the temperature goes to 0 as h bar goes to 0. Okay. All right. So this is good, because let's just think about thermodynamics for a moment. Suppose I have any thermodynamic object. Yes, question. Good. Let me get there. Let me say this first. I, in fact, want to talk about the second law right now. So let me first take the classical limit where there is no Hawking radiation. Okay? Because there's no Hawking radiation because the temperature goes to 0. And as we all know, if I have an object at 0 temperature, it doesn't send out any radiation. Right? Okay. So now, just think for a moment about any thermodynamic object which always has 0 temperature, no matter how much energy it contains, and which has infinite entropy. Okay? Well, it's always got 0 temperature. So that means that when you put it near anything else, energy flows into the 0 temperature object, right? Energy always flows from hot to cold. That's the way it works. So it absorbs all kinds of things and never sends anything back out. Sounds like a black hole, doesn't it? Indeed it does. Indeed it does. So it's very interesting that many properties of black holes in the classical limit are well reproduced just by any thermodynamic object. Okay. Also, let me do one more. Not only is S infinite, but as we said, ds was dm over t. And since t goes to 0, this also diverges. That is to say that the change in entropy between one black hole and the next larger one is also infinite. Okay? So what does that say about the second law? The second law says that entropy for the entire universe, if you like, universe, should not decrease in time. It should either get bigger or stay the same. Right? That's the second law of thermodynamics. Okay. Well, again, suppose h bar is 0, and there are black holes around. Okay. If there are black holes around, then if any black hole got smaller, or suppose there was one black hole in the universe, okay? If that black hole got smaller, its entropy would decrease by a negative infinite amount. And there's no way you could make up for that in any other process. Right? So the second law suggests that at least classically, the total surface area of all black holes put together should also be non-decreasing. It should also only get bigger as time passes. Okay? And this is a classic result in general relativity, which you can prove from the Einstein equations. It was proven by Stephen Hawking first. And so this is called the Hawking area theorem. Okay. It's true. It's just you can prove it in classical general relativity. So this is a certain bit of consistency of the whole story. I should mention for completeness that although this is called the Hawking area theorem, and Hawking proved the first version, it turns out the version he proved doesn't apply to the real world. Okay? It turns out the version he proved assumes too much about makes stronger assumptions about the horizon than are true in real life. However, this has been recently fixed in a lovely paper by Crucial, Galloway, and a few other collaborators. So you could look these folks up. So really, we should call it the Crucial, Galloway, something else, Hawking area theorem. But it's still called the Hawking area theorem. Okay. All right. So I'm just showing you that things fit together in the classical limit where h bar is 0. But what about the case, you say, where h bar is not 0? What does the second law say then? Well, when h bar is not 0, then the entropy of black holes is finite, and therefore black holes act much like any other object. The thing which is non-decreasing should be the total of the total entropy in black holes plus the total entropy in everything else, which we will call matter. Okay. So quantum mechanically, we expect that only this total needs to increase, which could happen in several ways. It could be that in some process, both these quantities increase. It could be, on the other hand, that the matter entropy shrinks and the black hole entropy grows. This is the kind of thing one is familiar with, because if, for example, we take a star and we throw it into a black hole, the star is now gone. So the matter entropy has gone down, because the star is gone. It's been eaten by the black hole. But the black hole gets bigger, and so it grows. Okay. But there's a third possibility as well, which would satisfy this. It's possible for the black hole to shrink quantum mechanically, so long as the entropy of other matter goes up by a correspondingly large amount. And that's exactly what happens in the Hawking process. In the Hawking process, negative energy comes into the black hole, so the black hole does in fact shrink. Okay? But as we said, the black hole throws out a large number of particles. And it throws them out as thermal radiation. And you may recall that thermal radiation has the most entropy that you can pack into a certain amount of energy. So it throws out a lot of entropy. And most importantly, it does this very slowly so that by the time the black hole radiates much of its energy, the first bit of Hawking radiation has traveled a very long way across the universe. So it not only emits this thermal radiation, but it spreads it across an enormously large region. And as you may know, whenever you have a gas or photons or what have you, and you allow them to fill up a very large volume, that generates a lot of entropy. Right? This is the famous adiabatic expansion of gases, that this configuration, where I have gas molecules all over a box, has more entropy than this configuration where I have them packed into a quarter. Okay? So the answer to your question, therefore, is the Hawking process satisfies the second law because it takes place in a large volume of space. And it disperses the radiation across a large volume. One can consider what happens if one does what's called black holes in boxes. You try to put the black hole in a small cavity so the radiation cannot disperse. In that case, the Hawking process, it's not quite correct to say that it stops, but what it does is it fills up the cavity with thermal radiation, and then the whole thing comes into equilibrium, and the black hole doesn't decay anymore because it has then reached its state of maximum entropy. Okay. For those of you who know anything about anti-de Sitter space, or the ADS-CFT correspondence that Clifford Johnson mentioned very briefly yesterday, anti-de Sitter space acts to a certain extent like a finite box, and this is what you find in anti-de Sitter space. A black hole in anti-de Sitter space, which is sufficiently large, knows that it's in a kind of box and remains stable and does not evaporate through the Hawking process because of the second law, because it would have to reduce its entropy to do so. Okay. Right. Okay. Good. So this is interesting. But perhaps the most interesting thing about the entropy of a black hole is just the fact that when h bar is not 0, we do have a finite result. Okay? Because, after all, let's see. This is where the real mystery is, in my opinion. It's why is the entropy of a black hole finite at all? Now, normally it's not a problem. If you have a system like a box of gas, you do a calculation of the entropy, it comes out finite, right? Why is that true? It's true because you do a calculation. Let's say you use what's called the microcanonical ensemble, which means maybe you fix the total energy. So you want to count the number of states with a certain energy inside the box. Well, if I try to add more particles, the energy goes up. If I try to make the particles, take the particles' wave functions and make them too narrow, the energy goes up. That's quantum mechanics. So it's the fact that you only allow a certain amount of energy that makes the number of states inside a box finite. Now, what about the black hole case? Well, certainly, again, we want to fix the energy. We have only this much energy to work with, that times c squared. But now we have a problem, which relates to our previous discussion. Because inside the black hole, there are both, as we said, positive and negative energy states. And if there are both positive and negative energy states, then it's hard to see why we can't keep adding particles that have positive energy and simultaneously add ones that have negative energy and let them cancel out and still have mass m. So this is a deep mystery. Black holes, in some sense, appear to have a finite number of states. And as I mentioned, the question is then, why should it be true? Or perhaps, is there some other interpretation of this entropy? Is it perhaps somehow possible that really the black hole has an infinite number of internal states, but somehow only a finite number count? That might be another logical possibility. And that's an open and sometimes hotly debated area of research. Okay. Other questions before I say a few minutes about holography? No? All right. So I was requested to say something about holography, and I will now do so, having gone through the appropriate background. So this term holography, let me just remind you where it comes from. Holography. It's related linguistically to the word hologram, which I would expect that probably you've all heard of. This is the process where you use lasers and interferometry to record a three-dimensional picture of an object on a two-dimensional piece of film. Okay. So, in fact, I probably even have one on my credit card someplace. Many people do these days. So this is a process that encodes three-dimensional information into two dimensions. And the point is that black holes remind some people of holograms. And why is that true? Well, we've been talking here about thermodynamics, right? Okay. Suppose one considers thermodynamics of an ordinary system. Thermodynamics of, let's say, of photons. Okay? Then suppose I give you a bunch of photons in a box, and I ask you, well, suppose I more properly take a box and heat it to some temperature. And I ask you, what is the entropy in this box? Then it's a standard thermodynamic calculation, I'll just write down the answer, that the entropy is roughly the temperature cubed times the volume of the box. Okay. Right. So, I guess I see that I missed a step, but I'll try to put this together in the right order. So one is used to seeing factors of volume appear in the entropy. Okay. In the black hole case, instead, what we see is the surface area of the black hole. So at the linguistic level, this word hologram relates to what you would have thought was a volume effect being replaced by an area. Okay. Now, to understand more the logic of why this is supposedly interesting, let me just remind you that it's very natural for black holes to have some kind of entropy. And why is that? Well, let's recall where entropy comes from in usual thermodynamics. Entropy comes from the fact that we don't know the detailed state of the system. Right? In usual thermodynamics, what we do is we say, aha, I know the total energy of the system, but I don't know the exact configuration of each of the little molecules of a gas. And then entropy, right, is the logarithm of the number of possible microstates which have that energy. Well, in a black hole, typically it's the same story. If you're sitting outside, you know the mass of the black hole because that determines its gravitational field, but you have no idea what happened inside because, as we said, you can't get any information out of the inside of a black hole. So it's very natural for black holes to have entropy. And one might think that it's natural for this black hole entropy. So let's see, I'll write this as a natural guess, is simply the logarithm of the total number of states inside the black hole. In other words, it is perhaps natural that you should think of this entropy of a black hole as being the counting all things that could possibly go on inside. Okay. And you might say, if it's counting all things that could possibly go on inside, maybe that means that you should do this counting without even assuming it's a black hole. Maybe, this is again further guess, maybe this is in fact the logarithm of all possible states inside a region with area A. So some people look at this, and some people, the person who usually pushes this kind of thing hardest is Lenny Susskind. There are others as well, but I will not possibly remember to list all the right names, so I'll put down a 1, which is indicative. You can look up his papers on the subject if you're interested. So this suggests to people like Lenny that perhaps it's true that, in fact, the real possible ways that you can arrange things in some region of space scales like the area and not the volume.
Would that
Yes?
be only positive energy states? Or
Well, now that's an interesting question. The usual intuition here is that somehow it's all possible things.
and then why isn't that infinite?
An excellent question. That is well, okay, good. So that is an excellent question. No one, excuse me, no one has a good answer to that question. Okay, but notice that's an issue with black hole entropy in general, and not an issue with holography per se. Okay, so in holography, people will say, well, there's some issue here which is very important that we sort out someday. Why is the number of states finite at all? But they jump ahead and they say, all right, let's take that as a given that it is finite through some mechanism we don't yet understand, and let's see what we can learn about other physics from that. Okay, so they say, all right, surely this, so they're guessing that in fact this number of possible states inside some region is also finite.
So why does that not hold for the box?
Because the box isn't big, because if you look at this logic, if this is to be true, most of the possible states associated with some region of space should be a black hole, if these two things are to be comparable. The box is not a black hole. We put that in by hand. So we've restricted ourselves to some tiny fraction of the possible states for a box. So the box would be a contradiction if the experimentally measured entropy of this box were larger than the entropy of a comparable black hole. But interestingly enough, that's not true. The black hole has much more entropy. So this is a plausible set of assumptions. Okay. Just to make one more thing clear, people in this business often talk about the entropy as counting what's called the number of degrees of freedom. Instead of saying it counts the log of the number of states. And just to give you a brief idea of what that means, imagine that we had n spins, each of which could take the value plus or minus 1/2. Okay? Well, so then one of these spins is something you would call a degree of freedom. It's something you can change about the system. Okay? And if I ask you, if I have n spins, each with 2 states, how many states are there for all n? Well, there are 2 to the n states, right? So therefore, the entropy is, roughly speaking, the log of 2 to the n log 2, whatever. So one often talks about the entropy as being proportional to the number of degrees of freedom. Okay. Similarly, suppose I had a box, and suppose I believed that this box was this, that suppose I had, let's say for simplicity, a fermion field. So the electron field inside this box. Okay? And suppose I believed that field theory, our usual field description, is a useful description, but not at the tiniest scales. Because maybe I believe that space-time does something funny on very small scales. Maybe due to quantum gravity, something like that. So suppose I believe that field theory is a good description only for lengths bigger than some cutoff. This is the cutoff that Tony Z talked about. Okay? And now if I asked you how many states are inside this box, well, I could find out by starting to divide the box. I could make a little grid here, and I could divide the box into smaller boxes. Okay? But I'm only allowed to make the boxes so small. I can make the boxes of size LC. Okay? And if I made them smaller, well, that's the cutoff. That's the smallest I'm allowed to make them. Okay? So there are therefore, in this thing, a large number of boxes. How many? Well, it's the volume divided by LC cubed. This is the fermion field. So roughly speaking, in each box, I can either have a particle or not have a particle. That's what we do with fermions. So the number of states is, again, 2 to the v over LC cubed. Or in other words, the entropy goes like the volume over LC cubed. Okay. And so this is where the great contrast comes in. The suggestion of holography is that somehow, due to gravity, due to black hole formation and so forth, the actual number of degrees of freedom in a box, again, scales not like the volume, but like the area. Okay? So the suggestion is that something that you would expect it to be three-dimensional is actually two-dimensional. And people might go on to further speculate that perhaps this could be true if some more fundamental description of our universe, including now gravity and its quantum effects, was actually something of lower dimension. That is to say, perhaps it's true that our universe is, as Lindy says, a hologram, or something that appears to be 3 space dimensions plus time, is better described as something that is only 2 space dimensions plus time. That's the basic idea of holography. Okay. I see that I'm rapidly approaching the end of my time, but let me say just one more thing. Holography is a subject much talked about, and you will find many vocal enthusiasts of holography, especially in the string theory community. I have recently been going around giving a series of talks about why one might be skeptical about holography. Okay. It may well be true. I don't mean to prove that it's incorrect, but as I said, it's merely a set of suggestions. And there are also counter-arguments to believe that it may not be true. I have discovered while giving these talks that there is a larger set of people than one might expect who were already skeptical of holography, but were less vocal than those who were believers in holography, just to alert you. I don't know how to count the relative numbers of such people, but there are a fair number on both sides. And why might you be skeptical of holography? Well, let's simply recall that let's start by recalling that this logic here was not in any way ironclad. For example, let's start with the first statement. The first statement here was that was a guess that what you're counting for the black hole is the total number of states that could possibly be there inside the black hole. Okay? But recall that even for a black hole, we know something about what's going on inside, because we, for example, know the mass of the black hole. So even, let's see if I can draw a picture. Even in a region inside the black hole, it's quite plausible that there are some things we could do in this region. Okay. There may be, well, I'll even say there are likely configurations of the inside with energy greater than mc squared. In other words, it seems quite plausible to me, at least, that there would be ways to set up the inside of a black hole, or the region of space. That is to say, it seems plausible to me that there are ways to set up the region of space inside a black hole, bounded by its surface area, which correspond not to the black hole one wanted, but to, for example, a larger black hole. And why not? That would be one way to avoid this series of holographic arguments. So anyway, this remains an interesting area of discussion and current research, and perhaps some of you will at some point be motivated to contribute to this discussion. In fact, I believe some of you already have in some sense. Good. All right. I am rapidly approaching the end of my hour. I think perhaps technically I have 4 minutes left, but let me stop here. This is a good point, and see if there are further questions. Nothing disproves anything here. So my only point was, here was a series of suggestive arguments, and I wish to simply point out what the possible loopholes are. So this was, the idea in this line of reasoning was that perhaps a black hole is what results when, as is often said, you excite some region of space as much as you possibly can. Okay? Well, I'm simply saying here, it's not a priori obvious that there is a maximal limit to the extent to which you can excite a given region of space. It's perhaps plausible that if you take a given region of space, you could excite it to arbitrarily high levels, and that would correspond not to one black hole, but the more you excite it, to the bigger black hole you would get. Okay? In this picture, so in the picture of holography, if one takes a black hole, so now I'll make this a black hole of size r. In this picture of holography, somehow when you have a black hole of size r, this region is maximally busy. There is no way you could do anything else inside this region. It's perhaps plausible, though, that a black hole typically does not look like that. Perhaps a black hole of size r typically has only some excitations, and in fact is sort of quiet near the outside. Why not? Or to say it differently, if you give me this configuration, which you believe is maximally excited here, well, what physical mechanism would prevent me from putting in one more long wavelength photon that just fits inside the black hole and adding a small amount of additional energy to the black hole? Now, there may be such a mechanism. I certainly haven't proven that there is not, because there are many parts of this we don't understand. But I simply wish to make it clear that holography is a research direction and an idea for black hole thermodynamics, and not in any way, as far as I can tell, a conclusion of what's known about black holes to date. Oh, yes. But that by itself is not holography. That's merely the entropy of a black hole. A over 4 is a calculation we can do. Black holes have an entropy A over 4. Yes?
I don't follow your argument either.
Okay.
So if I take the viewpoint that instead of seeing a region of space being maximally excited,
right,
I see in the development leading up to the black hole. So it reaches a point where I've got these highly excited modes that eventually become gravitationally unstable and I form a black hole. That just tells me that I can't know anything more about those higher states of excitation. Right?
I'm not sure I entirely followed that, but it sounded good.
But so in other words, I mean, what you're suggesting is that you can add more energy, or there are higher energy states available inside the black hole.
Right.
But I mean, won't this have an effect on the actual size of the black hole?
It has an effect on the size of the black hole. The question is that the same as what's being discussed here?
But I mean, they are tied with each other in a sense. Because I mean, as soon as the size gets bigger, then your area has to get bigger. So you in a sense, catering for that extra entropy that you add into the black hole.
The question is, let's see, how shall I put this? So the question is, if I excite some bit of states here, and they make a larger black hole around it, okay, do I get to count the small area that contains the stuff making the black hole, or am I forced to count the larger area of the black hole itself? Okay. And this is a question which I think is in principle unclear. If the black hole is in fact formed by things in a small region, then perhaps in principle one could talk about things in that smaller region. And in fact, if I was inside the black hole, It would be natural to do so. Because as we saw, if you fall into a black hole, you naturally enter a region where, in fact, the space itself shrinks. Right? You naturally enter a region where the space becomes very small. So indeed, even in a large black hole, if you fall into the black hole, you naturally enter a region where everything that made the black hole is contained in a much smaller size. Okay. Now, as perhaps is clear, this is not so much an argument as a discussion about what the rules are, how one should count things, etc. Okay. And good. So I just want to make it clear that that is sort of the state of the art, that people are discussing these things and wondering what the right rules are for studying effects involving black hole and quantum mechanics. Good. If I had a few, you feel free to ask me later about other pros and cons of holography. There is a large list of things that one can say to argue for holography. However, there is an equally long list one can give to argue against those things. So again, it's very much an area of open debate. I should say the summary is, as far as I am concerned, I find that there is no completely conclusive argument for holography. But on the other hand, neither is there a clean-cut example of a situation where it clearly fails. So this makes it a very interesting area for further research. All right. Great.
Let's end there. And thank Don for an excellent series of regular lectures, and then thank him for putting on this extra one. And we can probably field further questions on trips.
Absolutely. Absolutely. Absolutely.